Hey guys, so this is our second video for our Flip the Classroom lesson on conic sections on the polar plane. And in this video, we are going to look at graphing some conic sections on the polar plane. In the last video, we said we could define any conic section on the polar plane with a vertices at the origin opening vertically or horizontally with equations that look like this. R equals KE over 1 plus or minus the cosine theta, or R equals KE over 1 plus or minus the sine theta. And we said that if we saw cosine in the denominator, this was going to be a horizontally opening conic section. If we saw sine in the denominator, this was going to be a vertically opening conic section. So right here, what we're going to do first is go through and identify the conic section and the directrix. And then we're going to go through and graph the conic section on the polar plane by plugging in some theta values and getting some r values. So immediately right here, we want to remember that what's defining the conic section in these equations is the eccentricity, that e value. And we have the eccentricity as the coefficient of the sine or cosine in the denominator when we have a lead term of 1. So right here, for this first equation, we've got r equals 2 over 1 minus 1/2 sine theta. And we can see that that lead 1 in the denominator tells us that this 1/2 is going to be the eccentricity that defines this conic section. And that is an eccentricity of 1/2. Since that's a number less than 1, we can say that when we graph this, we're going to get the graph of an ellipse. So right here, if we want to define the directrix that corresponds to our focus on the origin, we can see that we've got that length of the focus to its corresponding directrix as k, as one of our two multiples in the numerator. So right here with the numerator KE, we can say that for this particular equation we have KE equals 2. And since we know the eccentricity is 1/2, we can say then that K times 1/2 equals 2, which gives us a K value of 4. So we know that the directrix is going to be 4 units away from the focus on the origin. And right here what we want to do now is take a look at the equation and sort of think about where that directrix is going to go. So first off, we can say that since we have sine in the denominator, we know we're going to be opening vertically. And since we're seeing subtraction in the denominator, we know we're going to be opening vertically onto the positive y-axis, which means that right here, that directrix is going to be down here. And that's going to be a directrix of y equals -4. Now, right here, we're sort of defining that directrix with a rectangular equation, right, with the y. But in general, what we want to remember is that the location of the directrix to the focus is independent of whether we're defining our points with polar coordinates or with rectangular coordinates. So we can still place our directrix right here, whether we're on the polar plane or whether we're on the xy axis. All right, so right here what we're going to do is plug in some theta values. We're going to go ahead and plug in easy theta values. So we're basically looking at rotations that stop on the axes. So we're talking about 0, pi over 2, pi, then right here we have 3/2 pi, and then 2 pi just for symmetry. And so right here, plugging in these rotations, we can say that for a rotation of 0, sine is 0. So right here we're going to have 2 divided by 1. We're going to get an r value of 2 for a rotation of 0. For a rotation of pi over 2, we are going to get a sine value of 1. So that's going to be 1 minus 1/2. And that gives us 2 divided by 1/2 as 4. For a pi value, or for a rotation of pi, right, so a half rotation, we can say that sine is going to be 0 again. So right here that gives us 2 divided by 1 for 2. We have a value of 2 for the rotation of pi. For 3/2 pi, we are going to have a sine value of -1, and that's going to give us 2 divided by 3 halves, which is going to give us 4 thirds, or 1.3 repeating. And then for the rotation of 2 pi, a full rotation, we get sine as 0 again, so that's going to give us a value of 2. Obviously, these 2 pairs of polar coordinates are going to sort of repeat a point there, but that's all right. All right, so let's go ahead and plot these points. So right here, starting at a rotation of 0, we've got an r value of positive 2, so we'll go out 2 in that direction. Now at a rotation of pi over 2, we've got an r value of 4, so we'll go 4 in the direction of pi over 2. For a rotation of pi, we've got an r value of 2, so we'll go out 2 in the direction of pi. And then right here, 3 halves pi is going to give us 1.33 repeating. So right here, we're approximately right there. That distance of 1.3 repeating in the direction of 3 halves pi. And then, of course, 2 pi gives us 2 again, so right here we're back to the same point we had over here. Okay, so right here what we have are basically some parameters to give us a rough sketch of our ellipse. It's not going to be perfect, but we can sort of sketch this guy out. Right here we're seeing an ellipse that looks like this guy right here a little bit, almost circular, really. And that's going to be a rough picture of our ellipse with that focus on the origin. So right here, what we're going to do is move on to our next polar equation, defining a conic. Right here we can see that with that lead 1 in the denominator, we have an eccentricity of 2 now, 2 greater than 1, so we can say that this guy is going to be a hyperbola. And for this hyperbola, we can define the directrix. Right here we can say that we know the numerator is ke, so right here we've got ke equals 2. And with an e value of 2, we can say that k times 2 equals 2, which gives us k equals 1. Now right here we can say, by looking at our denominator, we've got 1 plus 2 cosine theta. The fact that we've got a cosine tells us that we're opening horizontally, and the addition in our denominator tells us that we're opening onto the negative x-axis from that focus at the origin. So right here, with that k value of 1, we are going to have the line x equals 1 as the directrix to the focus at the origin. Okay, so right here, we're going to list those same rotations. But with the hyperbola, we actually have some interesting things happening. So we're going to leave some gaps in our table here. So right here we've got 0, we've got pi over 2, we've got pi, we've got 3 halves pi, and then we've got 2 pi. We can go ahead and plug in these rotations into the cosine in our denominator. For a rotation of 0, we have make that a little more clear and simple. For a rotation of 0, we've got cosine as 1, so that's going to be 2 divided by 3, so that's going to be 2 thirds is the r value for the rotation of 0. For the rotation of pi over 2, we've got cosine is 0, so that's going to give us 2 for the r value. For rotation of pi, we've got negative 1 for cosine, so that's going to give us negative 1 in the denominator. 2 divided by negative 1 is going to give us negative 2. And then right here for 3 halves, we're going to have cosine is 0 again, so that gives us 2 again. And then for 2 pi, we end up back at our 2 thirds. So right here, we can go ahead and plot these points. At a rotation of 0, we've got our 2 thirds, so approximately right there. Rotation of pi, or 2 pi, or pi divided by 2 rather, we've got the r value of 2. For the rotation of pi, we've got negative 2. So now we're going that distance of 2 in the opposite direction to define the point on our hyperbola. And right here for the rotation of 3 halves pi, we've got the r value of 2. And then, of course, we get 2 thirds again for the rotation of 2 pi. So right here, what we want to talk about is specifically what's happening in this interval and this interval right here. Because we have a denominator of 1 plus 2 cosine theta, right, where we've got 2 cosine theta potentially being greater than 1, we're actually going to get zeros in our denominator for certain rotations. And those rotations that will give us 0 in the denominator for our polar equation are going to be 2/3 pi and 4/3 pi. Now, of course, 0 in the denominator means we're undefined, but we don't want to think about this as necessarily r values that are undefined. We want to think about what's happening to the r values as we approach these rotations. As we approach the rotation of 2/3 pi, we're seeing this denominator get smaller and smaller. We're having smaller and smaller positive numbers in the denominator. So that means that we're going to be approaching positive infinity with our r values. And as we go past 2/3 pi, we're now getting really small negative values in the denominator. So we're going to be coming from negative infinity. For our 4/3 pi, right here, we're going to be having negative r values getting smaller and smaller, or we're going to have negative values getting smaller and smaller in the denominator, giving us larger and larger negative r values. So as we approach 4/3 pi, we're going to be approaching negative infinity there. And as we go past 4/3 pi, we're going to be dealing with small positive numbers in the denominator, so we're going to be coming from positive infinity with our r values. So right here, let's go ahead and think about what this graph is going to look like. So right here, we start out with the maximum cosine value, right, which is going to give us a maximum denominator of 3, and that starts us out right here at 2/3 for the r value. Now right here, as we rotate, we're basically seeing those cosine values become smaller and smaller positive numbers, and then they go to, then they're getting smaller and smaller still. Right here, this is our rotation of 2/3 pi. And so those denominators getting smaller and smaller give us larger and larger r values, and basically we're getting a graph of our hyperbola that's going to look like this. I'm going to draw this again so that we can see it a little more clearly. Approaching that 2/3 pi rotation, we get r values going out to positive infinity like that, right? Now after that, we've got r values coming from negative infinity. So for this amount of rotation right here, we're actually going to be getting r values that extend into the 4th quadrant, right? And we're going to be coming from negative infinity there. So it's going to come up like this. And all of these r values are negative r values, connecting to that negative r value of -2 for the rotation of pi. And then we get numbers in the denominator that are negative and getting smaller and smaller again as we approach the rotation of 4/3 pi. So right here for 4/3 pi, we are going to head out to that negative infinity r value. And then after that, we've got positive r values again. So right here, coming from positive r values now, we're going to be coming from 4/3 pi, where we follow that out infinitely. And we're going to get this side of the hyperbola like this. So this is a weird graph. Really what we're seeing here is, of course, an asymptote on the polar plane. We talked about asymptotes as being straight lines, but we can also see them right here with this hyperbola shape. And we're also going to see them in the parabola, right? So we're going to let you guys graph some of these on your own now. Right here, I'm going to let you guys go ahead and determine what kind of conic section we have, find and graph the directrix, and then go ahead and graph that conic section. We're going to use just the rotations that land on the axes to give us an idea of the conic section. Right here, what we're going to see, though, with the eccentricity of 1 is that, of course, this is a parabola. Okay? We've got the eccentricity of 1. And if we look at plugging in those rotations, we've got 0, pi over 2, pi, and then right here, 3/2 pi, and then 2 pi. At a rotation of 3/2 pi, right here, we're going to get a -1 for our cosine, which is going to give us 0 in the denominator. So this is where we're going to see that asymptote, right? And it's going to look a little bit weird, but the fact that you know it's a parabola and you're going to be able to define these other points, as well as the orientation of that parabola, should give you an idea of what this guy's going to look like. So we're going to pause the video here and let you guys give these two problems a shot, and we'll come back to it in a second. All right. All right, guys, so first what we have here is an ellipse, and we can see that because the eccentricity is 1/3, which is less than 1, giving us the shape of the ellipse for our equation r equals 4 over 1 plus 1/3 cosine theta. Right here, if we go over and we're asked for the directrix, we know that the numerator is going to be ke, so for a numerator of 4, we have k equals 4, and then we know that the e, the eccentricity, is 1/3. So right here we can say k times 1/3 gives us 4, and right here that's going to give us an eccentricity of, or a k value of 6 rather, and so that's going to give us the directrix as x equals 6. It's my mistake, actually. That shouldn't be 6, that should be 12. So as a matter of fact, right here, if we divide 4 by 1/3, we actually get a k value of 12, and that tells us right here that for our conic section opening on the negative x-axis, we have the directrix as x equals positive 12. So right here, that would be this ellipse. For the parabola right here, we can see with an eccentricity of 1, this is obviously going to be a parabola. We can determine the directrix by taking the numerator, setting it equal to ke. We know the eccentricity is 1, so that gives us a k value of 2. And right here we can say then that the directrix is going to be y equals 2, which we can graph right here. And then at this point, what we want to do is just sort of evaluate the rotations on the x-axis. So right here we can say that evaluating these rotations, we get a rotation of 0 giving us 2, rotation of pi over 2 giving us 1, rotation of pi giving us 2, and a rotation of 3/2 pi giving us basically an undefined value. But if we think about approaching 3/2 pi, we can see that that denominator of 1 plus sine theta is actually getting smaller and smaller. So we're getting r values extended out to positive infinity, right? And basically, as we continue to rotate, these r values down here are really, really long, and they continue to extend out, getting infinitely long as our rotation goes out, getting very, very long. And right here, we would essentially be undefined for the rotation of 3/2 pi, and then we'd basically be looking at those really large r values coming back on the other side of 3/2 pi. So we never actually get negative r values here, but we are getting r values that go out to positive infinity and then come back from positive infinity. And then right here, basically what we're seeing is those r values come back and end at 2 pi with an r value of 2. All right, so right here, this is the second video. We're going to do one more video, and then we will do a worksheet tomorrow. All right, guys. See you in the next video.